Hi, y'all stayed to the end. You're fabulous, you're wonderful. Thank you. It's going to be worth it. I designed this talk for 5 p.m., so just sit back and relax. I'm going to retro art and chill. So my name is Sherman. I have a two-word first name. Online forums and Starbucks are struggles. And I'm from Malaysia, a small Southeast Asian country, very far from here.
Malaysia boleh.
What?
Malaysia boleh.
Yeah, thank you. And I actually moved to New York to attend something called the Recurse Center, which is an educational retreat for programmers. Some recurses in the audience, hello. And if you want to fall in love again with programming, I highly recommend you check it out. I'm now working as a web platform engineer for a company called Teachers Pay Teachers, where I work on front-end infrastructure, so I write a lot of JavaScript. But recently I've been really into retro computer art, right? And it all started because someone showed me this website called the Recruit Project that houses a whole lot of magazine scans from the late 1970s of this particular magazine titled Computer Graphics and Art. And if you look at the title of one of the articles there, Inexpensive Graphics from a Storage Cathode Ray Tube, that really dates it. And this magazine was actually curated and edited by Grace Hartline from 1976 to 1978 before it got discontinued. And to give you a sampling of what the content was like, this was cutting edge graphics back in the 70s. And it's like black and white, really lo-fi, and today we will call it minimalist art, really edgy. And I was like, wow, this is like really cool stuff, it's really interesting. It's like, how were these made, right? So the whole premise of the Recruit project was that a lot of this art was published without the code that generated it. Most of the time the articles would discuss maybe the technologies and some methods, but no actual algorithms. So it's like, oh, you know, that's kind of interesting. Like, you know, can I reverse engineer it? Like, I wonder. So this entire talk will be kind of what I learned along the way. And we're going to start by talking a little bit about what computer art is. I'm going to try and find it. And then we're going to talk a little bit about what computers were like back then in the day. And then I'm going to show you some vintage art and different categories of them, and also attempts in recreating some of those pieces. So let's talk about computer art, right? What is computer art? So computer art, in my definition, is any art in which computers play a role in the production or the display of the artwork. And this can be something like using a computer as a digital canvas, so like good old Microsoft Paint. This is also vintage. And so you as an artist have full control over the artwork. It can be using computers to generate graphics, so you provide a set of rules and the definitions and let the computer use randomness to generate something that's not completely controlled by you, the human. It can also mean like training computers to learn different art styles and applying them. And these are like forms of computer art that we are familiar with today. But computer art back then, especially in this particular time period from the 1950s to the 1970s, it was very different back then. And the reason why I chose this time period is because this was way before personal computing. People didn't have computers at home. This was also a time before all these equipment or electronics that we now associate with personal computing, like colored LCD screens, or laser printers, or games, or 3D graphics. In fact, the first personal computer that is kind of iconic and well-known, the Apple II, was only introduced in the late 70s and gained popularity in the 80s. And 3D graphics was also introduced in the 80s. So this is way way before that. So yeah, to research this, there wasn't like a whole lot of information about early computer art online, so I actually had to go to the library and sit down and like borrow a book. And I couldn't even like check out the book because it was reference only, so that was cool, good times. Yeah, so computers back then, let me just give you a quick overview of what a computer would look like. And if you watch like old-timey movies, you might have like seen some of them. And so we're going to talk about IBM 7090 data processing system. It's not just a computer, it's a data processing system. It was huge, it filled up entire rooms. You can see here there are magnetic tape readers and stuff. And this was introduced in 1959, so quite a while back. for a very affordable price of $3 million US. And if you convert that to currency today, it will cost $18 million USD. So you can just like, ring up IBM like, I would like to buy one computer, please. I'll write you a check. So computers are really expensive and really big, and so not everyone could afford them. So most people who had computers were like large research institutions, universities, maybe government departments. It wasn't something that was accessible at all, right? So IBM 7090. Fun fact, NASA had one too, and we watched the movie Hidden Figures, which is a great movie, by the way. They had a 7090, and that was it featured in there. Good stuff. But most of the time, programmers wouldn't interact with these extremely large mainframes. What they would do instead was to sit at a specialized machine that it's kind of like a typewriter, but it punched holes in cards instead. And your code, you would type your code out on these punch cards, right? And what would happen is that you would type it out, put it in a little stack, and then give it to a little man behind the door, and 5 minutes later, you will get your output. So the next time you get impatient waiting for Webpack to build, think about this. So, good times. It's a different time, And so, back then, because these computers were so expensive and difficult to use, a lot of the times they were used for very practical reasons, like scientific and mathematical applications. And one of the pioneers in computer graphics actually was the Boeing company. And what they did was they would use computer graphics to visualize the movements of human limbs, to determine like where's the best place to place instruments in a cockpit. And this was like revolutionary at the time, right? This is like, whoa. And they also were the first to create animations of landing simulations. This is a model of the Seattle Tacoma Airport. And like these actually, even though they were used for practical scientific purposes, they actually like won design awards because people were like, whoa, cool. Its own aesthetic. And another company, and Boeing also, fun fact, coined the term computer graphics, so thank you. Another company that did a lot of research with the IBM 7090 was Bell Labs. That was in New Jersey, I believe. And Bell Labs also had a 7090, and with that, they made one of the very first computer-generated films. And I'm going to show it to you. All right, excited? Ready? And here it is. And it is a simulation of a 2-gyro gravity gradient attitude control system by Louis Zajac in 1963. And this was created, I believe, with a microfilm plotter. So it will draw like different frames on a microfilm, and then you can run it, and it will show you this. So this, yeah, good stuff. It's super cute. Basically, it shows a satellite orbiting a planet over time. So you're like, okay, cool, that's all really interesting and stuff. That's the practical applications. They have their own aesthetic value, even though it's like, oh well, we just want simple straight lines to demonstrate some models. But that became this whole aesthetic that we're going to see more of later. So it's important to note that a lot of the affordances that came about in computer graphics, so being able to draw lines and geometric shapes, all that came out of scientific need or purpose. And so those were the tools that people had to make art. So okay, vintage art. Let's do this. The first one I want to show you is oscilloscope art. And I have like emoji sets for like all of these, and they sometimes don't make sense, but they will once you have seen this talk. So oscilloscopes, right? Cathode ray oscilloscopes, to be precise, oscilloscopes. Back then, this is how they look like. This is a photo of an oscilloscope in the 50s. On the left here is this person, his name is Ben Lepofsky. I'll talk about his work in this section. And if you've ever been in a science lab or physics class, you've probably interacted with an oscilloscope, and they're like, there's a beam, it draws lines, it draws waves, cool. Basically, it takes in a signal, and it generates a wave. It generates a beam of light that hits a fluorescent screen, and that would give you like a dot or like a movement across your oscilloscope screen. And Ben Lepofsky was actually a mathematician who was like, hey, you know what? Like, this is kind of cool stuff. Like, let me see if I can like make something out of it. And so he was one of the first few people that decided to make art out of oscilloscopes. And it was actually inspired by music as well. And here are some of his works. He created a series of photographs titled Oscillons. And they were made by by using generated waveforms on oscilloscope screens. And to capture them, he would take a camera, put it in front of the oscilloscope. Guys, this is how this word is hard. Yeah, thank you. And he'll put a camera in front of an oscilloscope screen, and it will take a long exposure photograph. So what you're seeing is not like how the screen will look like, but how the waves will move across time on the screen. And I really like these because they have just a very ghostly, mysterious quality to them. And he actually published his work in in Recreational Mathematics, which is a magazine, in 1961, which cost 65 cents, very affordable to be a recreational mathematician. I wish I was like a recreational programmer, anyway. And so in it, he talks about how he would use color films to put in front of the camera to obtain color, because most screens were like just two-color, black and white back then. And they were made with a combination of different types of waves, so like sine waves, or like square waves, or the Sergio figures. And these were known by mathematicians back then to be like, oh, kind of interesting patterns. And if you kind of combine them together, you would get these really interesting figures. So unfortunately, none of the negatives of those photos remain, much less the algorithms or the formulas for them. So sad, because they're really interesting to look at. So I was like, well, could we perhaps try to recreate this with modern day tools that we have? And for that, I'm going to use something called EmpireJS, which is a JavaScript library that was created to make it easy to draw things on canvas. It's actually based off another language called processing that was introduced in the early 2000s. And the whole premise of processing, and also P5, was to make drawing with code accessible for non-programmers. So a very simple API, really intuitive to use, a lot easier than working straight on with Canvas. It has a great documentation, great website. I recommend you check it out. For the demos, I'm going to be using their P5JS editor in the browser. Also a great thing to check out if you just want to play around a bit. And so let's try to recreate this. So in P5, you can draw shapes, you can draw circles, for example. In this case, I'm drawing a little tiny circle in the middle of the screen. And I'm making I'm translating a little here to, so that the origin, the point 0, will be the center of the canvas. And that's great and all, but it's not so interesting. You want to also be able to make animations. So in order to do this, you can add a counter, let's say T over here, and increment it every time the frame is drawn. So P5 will call draw over and over again, and it will increment T, and if you plug that into the position of the ellipse here, which is this is the X and Y position, and this is the size of the ellipse, so position X0, 10 by 10 pixel size ellipse, which is a little tiny circle. So that's great, but to make things more interesting, we can make our ellipse or point move in more interesting fashions. And so if you plug in the formula for a circle, which is r sine theta for x and r cos theta for y, you get a circle being drawn. So the more interesting part actually comes from when modifying the theta, adding ratios to it, and this will give you a pretzel. And this is actually a form of the Sergio figure. And it gets even more interesting when you add a second point. So in this case, I added a second point that goes in an ellipse, right there in the middle. And it gets even more interesting when you draw lines between the two of them. And this kind of approximates that behavior that you see in the Portuguese oscillons. So if you combine all of that, that looks great and all, but it's drawing over and over the lines again, so it doesn't look that great. It gets really busy after a while. So if you kind of fade out the lines over time, this is what you get. And I want this as a screensaver. And so here I have this is the code. I'll tweet out the link to the slides later on. And all of this is embedded in the slides. So you can play around with it, you can edit it, you can run it. Feel free to make something out of this. So yeah, cool, Ocelot's got it. But I was like, okay, well, we can probably like take it a little bit further now that we actually have color screens. So this is what I have. Instead of drawing straight lines, I drew curves that move on sinusoidal forms and added a fill, a really transparent fill, and just drew the lines really close to one another. And this is what you get. That was also really fun. All right, so the next type of art that I want to share with you is plotter art. And a plotter, more specifically a mechanical plotter, is a machine that has a robot arm that moves on an XY plane. And what it does is that you can attach a pen to it and make it draw stuff for you. And so plotters are kind of limited. They can't really shade or create gradients. They can by just like cross-hatching lines. But a lot of plotter art that was really that was created back then were mostly like fine lines or very geometric. And you can see that kind of aesthetic in a lot of work. This is a modern day plotter. This is an AxiDraw that someone loaned to me kindly. And one of the types of art that I saw a lot was like geometric, and it involved like taking a square and like rotating it a little bit, making it a little small, rotating it a little bit to get this like kind of interesting swirly pattern. I saw this a lot, and I was like, okay, cool, that's interesting, whatever. And I later found out it was actually a visualization of a calculus problem called the 4 flies problem. So imagine 4 flies hanging out, sitting on a square table, facing inward. They all start simultaneously walking at the same rate, each directing its motion steadily towards the fly on the right. So they walk towards one another. Find the path of each. And while this is like, okay, cool, if I saw this like, without the visualization, that's okay and all. But when you actually start drawing it out, it's like, it really generates some really interesting patterns. And you can do this with as many flies. I'm not sure why flies, I just call them bugs. As many points as possible, and you get really interesting patterns. And I was like, oh, cool. And turns out, if you tile these shapes, like these are all triangles, and you tile them out, you get shapes that don't look like triangles at all. In fact, these look like spades. It's like, wow, that's awesome. And here's one with the squares, and it's like, wow, okay, that's not what you expect to see. So it's kind of interesting to see how problems that have a mathematical background can be visualized in ways that are really aesthetically pleasing. Wish I paid more attention in calculus class now. Yeah, so one artist who also used a plotter a lot was Vera Molnar. And she made computer art before computers were even a thing in the 60s. So what she would do is she would draw out patterns and randomize them in a grid, and she would create drafts, and sometimes she would write out the code for it and run it through a plotter, and like this will be a plotter version. So plotters at the time gave artists like a tool to work with that enabled them to run things that were like really repetitive, but also make it really consistent. And I think the interesting thing about Molnar's work is that she uses a combination of structure and chaos. So there's structure in the sense that there's a grid, but chaos in the sense that you have like randomness mixed in. And this makes for a really interesting combination. So like really simple graphics, just lines and shapes, but the idea of just like mixing, like putting these two contrasting things together yielded really interesting results. And it was also interesting to note that even in the early days when most of the computer art was made by mathematicians or scientists, like towards the 70s, computers actually became a lot more accessible to artists, and it afforded them another tool to create work. One of the pieces that I really like is 144 trapeziums, and I recreated it in P5 by drawing a grid. So it's a grid, and picking 4 random points to form the trapezium within a certain range, and just drawing them out. And because I'm using a computer, I can run it as many times as I want until I get something that I like. And this is a really nice affordance that we have today. Okay, the third and last type of art I want to show you is text-based art. And to talk about text-based art, we need to talk about printers. So printers, this was a IBM 1403 line printer that was attached to the IBM System 360, which is a more modern version of the IBM 7090. These things were huge, and this is a line printer specifically because it prints line by line. And there'll be a drum with a limited character set that you can print with. And these things were really fast. You know, you look at it, it's just like, they're also really loud, but I don't have volume on, so like, this is your sound effects. And because they're printed by line, you could just go. And an artist in the late 60s, Frederick Hammersley, who was actually an abstract artist, did a series of work that was printed using that very particular line printer. And you can tell it's printed because of the perforated edges of the paper. And I really like this because it's like, it's interesting to look at, and it's also more dimensional than what you expect like text-based art to be. And if you zoom into the details of his computer drawings, you can see like there are actually two characters at each spot. And that made use of the fact that you had a limited character set, but you can play around with different variations to create a sense of depth. And I really like that. So he actually continued using this style in his later works as well, in color. So you're like, okay, I've seen this before. This is ASCII art. We still have this, right? Yeah, not that retro. And is it really ASCII art though? Because it's more like EBCDIC art, which stands for Extended Binary Coded Decimal Interchange Code, which was the character set that was used by IBM computers at the time, and it was a much more limited character set. You can see at the top of this punch card over here, you have your numbers, you have your alphabets, and a set of symbols. And this was what was standard at the time for IBM computers. So it's even a smaller character set that you have here. This is a punch card, for those of you who have not seen it before. Fun fact, our 80 character line limit comes from punch cards. This has 80 characters across. And so I was like, okay, cool, well, let's like try and recreate this, right? So cool, what I have here is a grid, and each position in the grid, I drew over it with two different characters. But this is not just something that has to exist via printer. You can do more interesting things with it. So what if I wanted to animate it, right? So let's say I introduce the concept of time, and if I increment time at every frame, and I pass them into my functions that draw each character. So here, what I can do, I can maybe do T mod 65. 65 is the size of the rings that are being drawn. And ta-da, this is what I get. Printers can't do this. So I was very, very excited. So yeah, text-based art. And I found out later that Hammersley was working with something called the Art1 programming language, which was created by Catherine Nash and Richard Williams. Nash was a sculptor and artist, Williams was a computer engineer. And it was designed to teach students how to make simple computer graphics. They were trying really hard to make the computer more accessible to people. And the Art1 programming language was noted for its simplicity and intended primarily as an introduction to the use of computers for those without any technological background. And I was like, that sounds familiar, right? That sounds like P5. And so Art1 was the original P5. And to just like show you how far we've come, this is a piece of documentation on Art1. This is all you need to know to create an ellipse in it. You can type all this out onto a single punch card, and that will define the define the size and position of your ellipse, and it will print it out. And this is what you need today to draw an ellipse. And I was like, oh, it's such a different time. It's great. So it's kind of interesting how we get all this art made with the use of very limited technology that was not designed for use in creating art. But art persists anyway. You can always make something interesting and something beautiful with what you have. And yeah, I like computer art. And before I leave you, I want to share with you the first ever computer art exhibition in the US. Just a little disclaimer, this entire talk is very US focused, mostly because a lot of the documentation that was written for it was in English. There was also a whole movement of computer art in Europe. A lot of the books were in German. I don't speak or read German, unfortunately, so a little biased here in this talk. But yeah, the first ever computer art exhibition in the US was actually here in New York City at the Howard Weiss Gallery in 1965. It no longer exists, but it was somewhere on 50th Street, so not too far from here. The exhibit had works by Michael Knoll and Bela Hulas that were made with the IBM 7090. So Knoll and Hulas were actually engineers at Bell Labs, but the word Bell Labs never appeared anywhere in the exhibit because they were worried, like, what are you doing, like using this $3 million machine to make art? You know, like we don't want people knowing that. I mean, like today, if someone was like, can I borrow a computer to like make art? Yeah. So these are some photos of the exhibit. And really simple black and white drawings, like what we've seen before. And the New York Times actually reviewed it in a really small segment in 1965. And it wasn't very favorable. They were like, oh, well, it was very big, very geometrical patterns, excluding the smallest ingredient of manual sensibility. And like, it makes it sound like a bad thing, you know? And the joke is, one of the exhibits that was put up by Knoll was a recreation of Pierre Mondrian's composition with lines. And Pierre Mondrian was a pretty famous artist, works a lot of geometrical art, and he wrote code to approximate composition with lines. And so what he would do, you know, a little cheeky, is to show the computer version versus the original version to people. They actually did research with 100 people and asked them which one they preferred and which one was a computer one versus which was a human one. And found out that most people actually prefer the computer picture, so so you like what you like, you know, it's fine. And we've come a long way since. In fact, nowadays we have like entire galleries in museums celebrating computer art. There's one going on right now in London. I want to go. You should go if you can. And yeah, it's a great time to be alive for computer art. And that's all I have for you. You can find me on Twitter. My name is PirateFish. And if you enjoyed the talk, come and see me after this. I'll hang around. Yeah, you've been a great audience.